Good evening, everyone. I am Raul Samuel Norona on behalf of the Department of Statistics and Data Science of Christ Deemed to be University, Yeshwanthpur campus. I extend a warm welcome to all the participants, resource persons, and esteemed guests joining us today for this national level faculty development program on advanced statistical techniques for academic excellence on data analytics 2024 day 2. This 7-day program, designed to bridge the gap in advanced statistical methodologies, promises to enrich us with key insights into data analytics and its applications in academic excellence. Over the course of this program, participants will dive into critical topics such as time series analysis, regression, machine learning, generalized linear models, survival analysis, and much more, guided by a distinguished panel of experts. Today, on day 2, we will be dealing with the topic of generalized linear models. And it is my absolute pleasure to introduce our esteemed guest for today, who is also the organizer of this national level faculty development program, Dr. Shikhar Tyagi, a distinguished scholar and researcher in the field of statistics and data science. Dr. Tyagi currently serves as an assistant professor at the Department of Statistics and Data Science, Christ University, Bangalore Yeshwanthpur campus, where he continues to inspire and guide the next generation of statisticians and data scientists. Dr. Tyagi's academic journey is marked by excellence. He earned his PhD from Central University of Rajasthan, where his cutting edge research focused on frailty models for survival data, a crucial area within survival analysis that deals with modeling lifetimes and understanding dependencies between them. His research interests span across multiple advanced areas, including survival analysis, Coppola models, Bayesian inference, distribution theory, and applied statistics. With a remarkable publication record of over 36 research papers, Dr. Tyagi's work has been widely recognized in the academic community, both nationally and internationally. His contributions are not only theoretical but have practical implications, particularly in fields such as healthcare and public health, where survival models are crucial. Dr. Tyagi has collaborated with several prestigious institutions, and his research continues to push the boundaries of statistical theory and application. In addition to his scholarly contributions, Dr. Tyagi is a respected reviewer of numerous high impact journals. His expertise is sought after by journals such as Scientific Reports, BMC, Geriatrics, and Frontiers in Public Health, where he regularly reviews and refines groundbreaking research in the statistical and medical domains. Dr. Tyagi's excellence in teaching and research has earned him prestigious awards. Most recently, he was honored with the Best Young Faculty Award at 2023 International Conference on Research Methodology and the Best Young Researcher Award at the International Conference on Advanced Interdisciplinary Research. These accolades reflect his dedication to advancing knowledge in his field and his commitment to mentoring young researchers. Beyond his academic achievements, Dr. Tyagi is known for his collaborative spirit and his passion for integrating statistics into real world applications. His work bridges the gap between complex statistical theory and practical solutions, making a meaningful impact in various domains. We are truly fortunate to have Dr. Tyagi with us today to share his insights and knowledge. Please join me in extending a warm welcome to Dr. Shikhar Tyagi. A warm welcome to you, sir, and I hand over this session to you. Over to you, sir.
Thank you so much, Rahul, for such a great introduction. And good evening, everyone. Am I audible to all of you?
Yes, sir.
Yes,
Yes,
sir,
sir.
you are audible.
Yes, you're
Okay.
audible.
Okay, so we start our talk right now on the generalized linear model. The screen is visible to all.
Yes, sir, it's
Yes,
visible.
sir, it is visible.
Yeah. So we are going to talk about the generalized linear models because this time to shift our focus from the conventional linear model or multiple linear model to the generalized linear model. That will be our talk for today. These are the contents that I am going to cover in our uh, session. So first of all, we just do some recap about our previous talk, from the previous talk given by the Vishnuvardhan sir. I hope you just enjoyed that one. So in that one, we just understand what is the regression. So first of all, regression analysis is a tool of investigating the relationship between a dependent variable and one or more than independent variables. This technique is widely used in the predicting and forecasting. So basically, we have two, whenever we are going to study the two or more than two variables, so we are always interested in to check that is there any relationship between them or not. So for that one, to check that their relationship, we have two basically tools. First is the correlation and second is regression. So first difference between the regression and correlation is that correlation just tell us the relation between them. There is a positive relation or negative relation, or there is no relation, they are independent. But how much dependency, or how much what kind of relation they are having, and so that we cannot find out through the correlations. For that one we need the regression analysis, because regression is the mathematical functional relationship between these variables. So for that one, the regression analysis is basically applicable in the economics, management, life and biological sciences, physical and chemical sciences, engineering, etc. And in that one, scatter plot is the essential tool for checking the correlation that, as Professor Vishnuvardhan discussed yesterday about it. So a linear, simple linear regression model assume a linear relationship between a single regression variable x and the response variable y, and the model is given by the y equals to beta naught plus beta 1 x plus epsilon, where uh, y is the response variable or the random variable, and regression is also correlated controlled variable x, and beta naught is the intercept and beta 1 is slope, and epsilon is the error component, that as Professor Vardhan discussed in a detail. So there were some assumptions regarding the linear regression model. That is, first assumption is that the error term should be a random variable with mean 0 and some constant variance sigma square. That means it should follow the condition of the homoscedasticity. And second is the no autocorrelation between the errors, means errors should be independently identically distributed. uh, After that, error terms are independently normally distributed. That shows that the value of expected value of yi is equals to beta naught plus beta 1 xi. It is because here we are assuming xi is a constant term that we already know. So that's why we are showing it as a constant term, and the variance of yi is the sigma square, that is equivalent to the variance of error term. So the line fitted by the least square method minimize the sum of square of the residuals uh, between the object value and the predicted values. So objective of the regression is that to understand the relationship of the variables under consideration, to form the regression equation of the relationship, and to predict the values of the response variable for a given set of the values of explanatory variables, and to utilize the information in any policy formulation. So now we have a different type of regression model. First one is the simple linear regression model, where we have the linear relationship between independent and dependent variable. After that, we have the polynomial regression, predicting the quantitative response variable from a quantitative explanatory variable, where the relationship is modeled as the nth order polynomial. After that, multiple linear regression there, predicting the quantitative response variable from the two or more than two explanatory variables. Then we have the multivariate regression, that is predicting the more than one response variable from the one or more than one explanatory variables. See, in the multiple linear regression and the simple linear regression, we have only one dependent variable. In the multivariate regression, we handling more than one dependent variables. After that, we have the logistic regression, predicting the categorical response variables from one and more than one explanatory variables. And then Poisson regression is there, predicting the response variable, representing the count of from the one or more than one explanatory variables. After that, recently, it is very famous nowadays. That is called as the Cox proportion hazard model, predicting the time to event data, death, failure, or relapse from one or more than one uh, independent variables. And then we have the time series, basically modeling the time series data with correlated errors. And non-linear regression, we are having predicting the quantitative response variables from one or more than one explanatory variable where the form of the model is non-linear. These models are basically used when we have the threshold effects in the of the independent variables on the um, dependent variable. And then after that, we have the non-parametric regression model, predicting the quantitative response variables from the one and more than one explanatory variable, where the form of the model derived from the data, not the specified prior distribution. Basically, sometimes we have the data where we cannot fit the model, or we are not aware with the distribution family of the model. So at that time, we cannot fit any particular distribution, normal or other distribution, exponential, gamma, to the dependent variable. And in that case, we should move to the non-parametric regression. After that, the robust regression is there, that is predicting the quantitative response variable from more than one or more than one explanatory variable, using the approach that resists to the effect of the influent variables. These are the few famous regression models are there. After that, the flow chart, how should we apply the regression model? That is basically we should start and formulate the problem, and we choose the set of the variable, and based on that set of variables, we should choose the model and choose the method of fitting, and we should specify the assumptions. And after that, we should after checking the that one, we should go for the model fitting. And by using the method like OLS and maximum likelihood, others methods are there, and we should validate our assumptions through the residual plots, outliers detection, or sensitivity analysis. In that one, if the assumptions validation is fine, model is going to fulfill all the assumptions, we will move further. Otherwise, we just start again, and we just go for the different model from here if the assumptions are not going to be fulfilled in this one. If it is going to be fulfilled, then we will evaluate the fitted model, and we check the goodness of it to check the accuracy and the AIC BIC of the model, and adjusted R square and other things. And if it is okay, so we just go for the uh, our analysis part, and the we go for the interpretation of our results and validation of our results. That is the thing. Otherwise, we need to, if we are going to be failed again, we need to start with the different models. Now, let's start with a discussion. We have a one data set of the kidney infection data. In this data set, we have the 38 patients. All right. In that one, we have the catheter until it removed from owing the infection. So basically, they are inserting the catheter to the patients. It is till the infection is not going to removed. All right. So in that one, we have the time basically up to where the infection is not going to removed. And after that, we have few independent variables like the recurrence of the covariates such as the age, the gender, basically sex, and the three indicator variables GN, AN, and PKD. These three are GN, AN, PKD are the basically the different kind of kidney disease. In that one, this is the data set. If the data set is visible to all,
Yes, sir, it's visible.
okay. So in this one, we have the time one is a time one is a dependent variable where we have the time of inserting the Catherine to the patients, how many days it took to remove the infection. And after that we have the age of the patients, their gender. 0 is showing for the male and 1 is showing for the female. And we have the three different disease. 0 is showing that there is no the gn is not there. 1 is showing that a gn disease is there. Similarly an and pkd is there. So now suppose we have the time 1 as a dependent variable, and age, sex, an, gn and pkd are the independent variable. We want to see the mathematical functional relation between the dependent and independent variable. So which method we should use here? Can you tell me? I just show you the data again. This is the data. Values are there, and these are the age, sex, gn, an and pkd are the independent variable. Which model we should use here? So basically what happened most of the time when people are having the independent variable and dependent variable and the independent variable, they simply go for the multiple linear regression, because we have the more than one independent variables. So as sir said earlier, we should check the assumptions in the previous lecture. So we are going to check the histogram of the dependent variable. See, if we just see that most of the patients are taking the very less time between 0 to 100, and after that between 100 to 200 few patients are there, around 10 patients are there, and after that one patient is taking between 200 to 300 days, and two patients are taking between 400 to 500 and 500 to 600 days uh, to be cured from the kidney infection. So if we just see it, it is basically the positively skewed, right? It is positively skewed. So it is going to violate the assumption of y should be normally distributed from the simple linear regression. But second assumption is going to be fulfilled. That is showing that in the ACF plot we are seeing there is no autocorrelation between the observations, time observations. In that time one, there is no autocorrelation between them. So they are independent. They are not dependent on the each other values. So, but first assumption is going to be violated. So two assumptions are there that are violating that. Basically the normal response y is not normally distributed, and second may be possible that uh, error should not be normally distributed. When these two assumptions are going to be violated, so there are few possible ways of the variables, dependent variables, that are possible. First is y is dichotomous. That means y takes the values 0 or 1. In that one, we have the few examples are the email spam detection. That is basically you are going to predict if the email is spam or not. Second one is that credit card fraud. In that one, predicting if the given credit card transaction is fraud or not. That will you can denote with 0 or 1. In the health, predicting if the given mass of the tissue is being or malignant. So in that one, 0 and 1 you can show marketing, predicting if the given user will buy an insurance product or not. All right. So that also can be represented at 0 1, because as we know that we in the statistics we never uh, entertain the qualitative data. We need to for the during the analysis time we need to convert into the numbers, either 0 1 2 3 or 0 1. And the last one is the banking, predicting the if the customers will default on a loan or not. That will be the few examples of your dichotomous variable. Second will be if y is count number of counts or not in that one. Suppose first is the traffic safety, predicting the number of road accidents happening per day or per month basis. And second is the health, related to the health, that is basically predicting the number of the cases reported of a disease, right, on monthly basis or the daily basis, all right, in particular state or in particular country or in particular hospital. After that, the insurance, predicting the number of claims from the insured people in particular insurance company, all right. After that, the banking, predicting the number of credit card, debit card per customer in from the one particular bank. That will be the number of counts will be there. Third one is the y is the percentage or the proportion. Means y is going to lie between 0 and 1. From the health, again we have the another example, that is the predicting the percentage of the relief of pain and sleep using a drug. Or second is the economics. From the economics, the predicting the percentage of the total income spent on food. Another one, that is the marketing. From the marketing, that is showing the predicting the uh, percentage of the sales of small cars. From the education, we have the another example, predicting the annual proportion of male and female enrolled in a higher education. Fourth possible way is that y is a survival time or lifetime. That means it is going to lie between 0 to infinity, right? So in that one, we have the few examples. First, from the health again, that is the predicting the survival time of the patients suffering from cancer. All right, means how much time they are suffering from the cancer. That time will lie between 0 to infinity and the continuous variable. And then from the reliability, we have the predicting the failure time of a mechanical component or some particular machine. All right, that will be considered as a survival time. In the from the service, that is predicting the waiting time of a customer at a service station. How much time they need to wait at the service station, that will be considered as a survival time. Hydrology, basically predicting the waiting rainfall or maximum flood level. That is the another example from the survival time. So from these four, basically what is thing is there in the first one, that is the dichotomous. We it should be follow the binomial distribution most according to the situation, or the negative binomial distribution or hypergeometric, or uh, our geometric distribution. And for the y should be the count. For second one, it should follow the Poisson distribution in the that theoretically. So if we just see these two figures of the PMF of the binomial distribution, PMF of the Poisson distribution, so we can see that point on the points, it is not exactly normal in the both graphs. So definitely it is going to violate the assumption of normal, that y should normally distributed. So it is going to violate that assumption. All right. And third one is that percentage proportion basically lies between 0 to 1. In that one, it should follow the uh, beta distribution. And for the survival time, it should follow any lifetime distribution like gamma, Weibull, exponential, log normal, and other distributions are there. It should follow that one. So here we can see this is the basically the shape of the beta distribution under the different combination of the parameters, value of alpha and beta. We have the different forms, that is basically the positively skewed or negatively skewed, both are there, but it is not exactly normal. And here we have the Weibull distribution, that is for the different combination of the parameters k and lambda. We have the different shape, that is basically the heavy tail. All right, heavy tail is also one thing that we mostly see in the survival data or insurance data, where we have the few values that are extremely high, but not the outliers exactly, but they are extremely high. in compared to the other values. As we see in this data set that we I have shown here, most of the values of the T1 is lie between 0 to 100 and 0 to 200, but two values are there that are between 400 to 500 and 500 to 600. So these are extreme values. For that one, we need the heavy tail. That is definitely not the normal distribution. All right, so they are going to violate the assumptions. So in that case, we need to move to the generalized linear model. In that one, thing is that the GLM is basically the unification of the both linear and non-linear regression model that allow the incorporation of non-normal response distribution from the exponential family. All right, in that one thing is that first thing, assume the distribution, the response variable y is assumed to follow a distribution from the exponential family which allows for the modeling various type of data. For example, binary count or continuous, as we have discussed earlier. Independence should be there, means the observation are assumed to be independent, permitting the valid statistical inference through the maximum likelihood estimation. All right, we are not violating the assumption of the independence here also. All right, the linear relationship in the transform space. All right, even though the relationship between the predictor and response value may not be linear, but it should be linear when we are going to apply the transformation on the response variable through some link functions that we are going to discuss now, the about the link function and the parameter estimation. GLM utilize the MLE for parameter estimation and allowing for the robust method for handling the variability of the distributional assumption in the data. So basically, y should follow some distribution that is basically the from the exponential family, and we assume that it should be expected value of y for given x should be equals to mu, that we are going to assume in that one. After that, we need some link function. Why we need the link function? Basically, when we are going to define the
Hello, please hide that
yes,
screen presenting tab.
yes,
Please hide that presenting tab.
I didn't get may.
You can continue, sir. No issues.
Okay. So basically, what happened when we just talk about the generalized linear model? It is basically our uh, ex- uh, multiple multiple linear regression only. But thing is that in the multiple linear regression model, y is a y is a continuous random variable that lies between minus infinity to infinity, that can take the range between minus infinity to infinity. But we have the certain situations here, as we have seen earlier. We have the first different situation. First is that it is going to take the value between zero, either 0 or 1, right? But earlier the range of y is minus infinity to infinity. So now we need to transform the our dependent variable y in such a form that it should take the value with either 0 or 1. All right, and second situation is that it should be the count. So again we need to transform our dependent variable in such a way so it can take the value as a count, and third between 0 and 1, and fourth one is it should take the value between 0 to infinity instead of taking the value between minus infinity to infinity. So for that one, we need some link function. So GLM utilize a link function to relate the linear predictor to the mean of the response variable, because we are assuming that it is going to follow a random variable. So this allows the modeling the non-linear relationship between the predictors and the response variables while keeping the relationship linear in terms of the parameters. So traditional linear model do not incorporate such a mechanism. So maintaining a strict linear relationship through that one. So assuming g mu, g dot we are assuming as a link function. So in that one, G mu should be equivalent to the x beta, where x is showing the vector, not the individual variable. It's a vector of independent variables x1, x2, xn, and beta is the vector of the coefficient, respective coefficient, that is basically the beta 1, beta 2 up to beta n. So mu should be equivalent to the G inverse x beta in that case. So we need to transform the our dependent variable in such a way that mu, the mean of the response variable mu should be equivalent to the G inverse of x beta. In that case, if mu is going to lie between 0 and 1, in that one we have the several uh, link function. First of all is the logit link function. In that one, it is basically we are going to take log of mu divided by 1 minus mu, that should be equivalent to the x beta, or mu can be written as the 1 upon 1 plus e raised to the power x beta, that is also known as the sigmoid function. All right, famously, and other is the phi inverse mu, that is the probit link function. So x beta should be equivalent to the mu. Mu should be equivalent to the phi x beta, that relate to the probability, or the log link function is there, that is basically log of minus log mu equals to the x beta, that is basically mu should be equivalent to the e raised to the power minus e raised to the power x beta. Or complementary of the log link function is also there, where we are going to take the log of minus log 1 minus mu, that is equivalent to the x beta. So mu should be equivalent to the 1 minus e raised to the power minus e raised to the power x beta. That are the four possible ways that we can take, but most popular way of doing taking the link function in the logistic case, or the when it is going to take the value between 0 and 1, that is mu log of mu upon 1 minus mu, that is basically the logit link function or the sigmoid function. If it is going to between 0 to infinity mu, at that time we have the log link function, that is log mu should be equals to the x beta. So mu should be equivalent to the e raised to the power x beta, that we can use. If mu is going to lie between minus infinity to infinity, at that time we can use mu equals to x beta, that is the identity link function that is similar there in the linear regression model. At that time we don't need to transform it, the dependent variable. So now we just talk about the logistic regression, that is basically regression model for the dictomous variable. So in that one we have dictomous variable y, that is going to take the value 1 with the probability pi, or it takes the value 0 with the probability 1 minus pi. All right. For example, success, failure, defective, non-defective, present or absent of a disease, that is basically the few possible cases for the dictomous variable. So in that one, variable y can be uh, governed through the Bernoulli law. All right. In that one, we already know the PMF of the Bernoulli distribution, that is basically p raised to the power y 1 minus p raised to the power 1 minus y, and y will take the value either 0 or 1, right? So under the assumption of the linear model that we have discussed earlier, so epsilon I should be equals to 1 minus x beta when y equals to 1. Basically what we write it as y equals to beta naught plus beta 1 x1, so plus epsilon, so epsilon equals to y minus beta naught plus beta 1, sorry, minus beta 1 x1. So y is going to take the value 1, so at that time it will become 1 minus x beta, and if y is going to be 0, so it will take the value minus x beta. That will be our error term under the dictomous variable. All right. So that will be the sigmoid curve. If x is going to between minus infinity to infinity, and you are going to use the one up this transformation 1 upon 1 plus e raised to the power fx, so it is going to lie between 0 and 1. All right, it will not go beyond that one. So now what will be the mean response in that term when it is going to be dictomous? So expected value of yi, what it will be for the Bernoulli case, it will be summation xi into pi. So yi into pi. So y is going to take 1. So probability will be 1. If it is y going to take the value 0, then the probability will be 1 minus p. So definitely the expected value of yi will be equivalent to the pi. All right. In that, after that, we have the joint distribution function, that is basically we called it as a likelihood function. We will take the likelihood function. In that one, it will be summation I goes to 1 to n yi log 1 upon pi divided by 1 minus pi. All right. So in that case, what will happen when y is going to take the value 0? So the data point where the outcome y is 0, the probability of the observing the outcome is maximized when the probability is equals to 0. So in that case, p cap will be equivalent to 0, definitely. And if you are going to put it in the log likelihood function, so it will becomes log of 1 minus pi. All right. And log 1 minus pi, if you are going to put, so log 1 minus 0. So that means it will be 0 only. All right. And when y is going to be 1, so definitely it is going to be the observing the outcome that is maximized when the p equals to 1. In different other words, based on the uh, our mean response, p cap will be equals to the yi, that is equals to 1, and substituting the pi equals to 1 into the log likelihood function here, so it will be equivalent to the it will equivalent to the 1, oh sorry, pi cap. All right. So this kind of model is referred to as the saturated model. So basically, what is the saturated model? Include a separate parameter for every unique combination of the predicted variable, effectively fitting on the model exactly to the observed outcomes. That means basically a data set with the n observed value and p predicted predictor variables. The model can fully capture the all variation in the data, essentially fitting the probability of the outcome y to either 0 or 1, depending on the input of the values of the predictors. After using this logistic link function, so log pi upon 1 minus pi will be equivalent to the xi dash beta. That is basically equivalent to the beta naught plus, so it is beta 1 xi. It is wrongly written. So log likelihood function will becomes summation of yi xi dash beta minus summation of log of 1 plus e raised to the power x dash beta, when you are going to take the log of the likelihood function. So if it is two independent variable, then it is fine. It will be like yi equals to the beta naught plus beta 1 x1i plus beta 2 x2i plus log of 1 plus e raised to the power beta naught plus beta 1 x1 plus beta 2 x2. And you can maximize the likelihood function by differentiating with respect to the beta naught, beta 1, and beta 2. But problem starts when it is you are having the more than 2 or 3 independent variables. So at that time, what will happen? Beta 1, beta is will occur in the beta j's MLE. So at that time, we cannot find out the likelihood in the closed form. At that time, we need some numerical method like Newton's action or accept reject method and some other methods to find out the nonlinear method to find out the MLE of the betas. So now the things comes basically about the log odds. How we are going to take the decision about the model. So basically, it will not come in the form of x y equals to beta naught plus beta 1x. It will come in the form of log of p 1 upon 1 p upon 1 minus p equals to beta naught plus beta 1x. That is basically called as the log odds of x. So directly in the linear regression, we says that beta 1 is whatever the value of beta 1 we are having, say beta 1 cap. So we says that changing the 1 unit in x, we find the beta 1 cap changes in the value of y, but it is not like that here. It will be basically like that. If the 1 unit change in x of the results of beta 1, uh, units change in the log odds of x. Also, you can say it if the p is, you are going to put the value of p is equals to 0. 0.5. So log odds of x will be equals to 0, because 0.5 upon 1 minus 0.5 will be equals to log 1. And we know that the value of log 1 is basically 0. All right. So, or if it is greater than 0.5, so basically 0.5 upon 1 minus above value, that is greater than 0.5, so denominator will be less, so you will get the log odds greater than 0. That is basically says that the probability of success is greater than 50%. So odds are greater than 1, resulting in the positive log odds. If p is less than 0.5, so that means the probability of success less than 50%, hence the log odds p upon 1 minus p is less than 1. This results in the negative log odds. All right. So now comes to the odds x plus 1 and divided by the odds x, that is basically the exponential of the beta 1. Exponential beta 1 is estimated increasing the probability of success when the value of explanatory variable change by 1 unit. Basically, it means that this formula represents the odd ratio, which tells us how the odds of the success change when the explanatory variable, independent variable x, increase by 1 unit. That exponential beta 1 basically shows that the coefficient of x, which gives the multiplicative change in the odds of each unit increasing in x. All right, that is the another way of interpreting the results. In this one, if exponential of beta 1 is greater than 1, basically it means that increase in the unit, for each unit increase in x, the log odds are multiplied by a factor greater than 1. This indicates the positive relation between the x and the likelihood success. And when beta 1, exponential of the beta 1 is going to equals to 1, that is basically is going to show that, that means beta equals to 0. All right, that is going to show that the odds of the success remain unchanged when the x is going to increase by 1 unit. But if exponential of beta 1 is less than 1, that means beta 1 is going to be less than 1. That means the each unit increase in the x, the odds of the success of multiplied by a factor less than 1. This indicates the negative relation between the x and the likelihood of the success. All right, that is basically the odds. After that, after finding the estimate of the interpreter of beta naught and beta 1, we just go to the goodness of fit. All right, uh, for the goodness of fit in the residual, we have the one thing that is called as the residual deviance. Residual deviance is nothing but the equals to the minus 2 log of saturated model minus log model with the covariate. That is basically, saturated model means a model that fit the data perfectly with one parameter per observation. All right, but the model with the covariate, that logistic regression model with the all the explanatory variables that we are going to take, that is basically the model with the covariates. And since the log likelihood of the saturated model is typically 0, as we have seen earlier, the residual deviance simplifies that it should be equals to the minus 2 of log of model with the covariates. All right, in that one, the null hypothesis is that y should follow the some particular distribution, basically the Bernoulli distribution with parameter pi, against the alternative hypothesis that y should follow the distribution with the including the parameters. of the basically the coefficient of the independent variables, beta naught, beta 1, and beta pi. All right. So in that one, it should follow the chi-square distribution with n minus p degree of freedom. All right, where x is the number of n is the number of observation. All right, and p is the basically that one number of independent variables. All right, so that basically gives us the individual contribution of overall deviation of each data point. That is the thing. In the null deviance is there. In that one, null deviance basically measures the how well the our simplest possible model, basically a model with only the intercept and not having any explanatory variable fits in the data. This model assumes that the possibility of the success is constant for all observations. That means there is no variations in x basically. So the null deviance is calculated as the deviance equals to minus 2 log of likelihood of saturated model minus log of likelihood of the model with the intercept only. All right, that should follow the chi-square distribution with n minus 1 degree of freedom. All right. So after that, we are going to take the difference between the null deviance and the residual deviance. All right, which follows the chi-square distribution with p minus degree of freedom. All right. Uh, this basically this difference of the is showing that the basically this difference that we are taking, that is basically used to test whether the model with the explanatory variable fits significantly better than the null model, basically the model with the only intercept or not. That is the basically main purpose of doing this goodness of fit here. After that, we have the confusion matrix here that we are going to use for our further use. That is basically going to show us uh, means how many true negative, true positive, or false positive or false negatives are there in our data. That is basically can be described as the based on the performance of the classification of the model on a set of the test data. We compare the actual target values with the predicted values. All right, that is called as the basically the confusion matrix. In that one, we have the true positive. All right, here true values, predicted values are there. In that one, we have the true positive, false negative, false positive, false negative. What is true positive? A true positive is basically these are the instance where the model predict the one, basically the positive class, that actually class is also one. For example, suppose that we are predicting the whether a person has a disease or not, and we are showing that the disease is showing by one, presence of the disease is showing by one, and zero is showing the there is no disease. If the model predict that the person is having a disease, so that is called as the true positive. All right, and true negative is basically that we are going to test that there is actual negative is there or not. All right, because we are taking the values between 0 and 1. So if actual 0 it is showing, then it is calls as the true negative. In the same example, if we are saying the prediction of the disease, if the model predicts the person is not having the disease and person is not having actually disease, so that is called as the true negative. All right, in that one, false positive is there. That is basically also known as the type 1 error. That if you have studied the statistical inference, so you will be aware about that. In that one, if the model is going to predict that the person is having a disease even though it person doesn't have the disease, so that is calls as the false positive. All right. And after that, we are having the uh, false negative, that is basically called as the type 2 error in the statistical inference. So if the model is going to predict that the person is having doesn't have the disease basically, and actually present patients is having the disease. All right. So this is called as the false negative. All right. These two things are very serious in the field of the medical. All right. That can lead us to very uh, bad or kind of very crucial stage where that wrong decision can lead us to the very uh, different kind of very serious situation. So these are that much of problematic at that time. So now our why we need the confusion matrix. Confusion matrix help us to find out the accuracy of the model. All right. So accuracy can be find out through the formula of true positive plus true negative divided by the total number of cases. All right. After that, precision we can find out of the proportion, basically the proportion of the positive values that were correctly identified. That is basically true positive divided by the true positive plus false positive. All right. In that one, after that sensitivity we can find out the proportion of basically the proportion of the actual positive cases that are correctly identified. So it is basically equals to the true positive divided by the
Sir,
true
excuse
positive
me.
plus.
Sir, excuse me. In the
Yes, sir.
formula, both are sensitivity and specificity, both are actually same, sir. Written as true
Uh,
positive or true positive divided plus false negative, and the specificity also it
oh,
is
sorry, sir. That is wrong. I just yeah, it is
same.
not exact, sir. All right. So in that one, true positive plus false negatives are there in that one. All right. Specificity is basically the true positive cases. All right, divided by the true positive plus false positive. Specificity it is false positive, not false negative, basically. All right. So after that we can measure the f1, that is basically the harmonic mean of the precision and the sensitivity. It gives
Sir,
the importance. Yes, sir.
excuse me, sir. Sir, specificity will be true negative divided by true negative and this.
Oh, sorry. Yes, sir. True negative, true negativity divided by the true positivity plus false positivity. Yeah, correct, sir. I just modify it and I will send the that modified PPT to all of you. All right, I will change it. All right. So now, after that, we have the another thing that is quite crucial for us in the logistic regression. That is called as the ROC curve. All right. ROC curve is basically is going to have the area under the curve of the receiver operating characteristics curve is a way to measure the performance of the predictive models. All right. In that one, how we are going to do it? Basically, uh, we are going to put the true positive rate or the sensitivity on the y-axis and false positive rate or on the x-axis. All right. That basically true positive rate is basically the true positive cases divided by the true positive plus false negative. And as sir just mentioned, rectified me here, the false positive rate is basically the false positives divided by the false positive plus the true negatives. All right, so the area is going to cover under this one. That is ROC curve. It provides the singular scalar values that summarize the performance of our model. All right, so AUC score is basically there. That is, if it is equals to 1, so we says that model is that distinguish between classes with no error. It is the perfect model if it is going to take the value exactly 1. If it is going to take the value around 0.5, so model random model is basically with the not no discriminative power, basically equivalent to flipping a coin. All right. If ROC is, AUC value is going to below 0.5, the model is not good enough. All right, or model is the worst to predict the things. That is the thing basically. In general form, basically we says that if the value of AUC is between 0. To 0.8, we say that model is performing acceptable. Model can be accepted. If the value is between 0.8 to 0.9, model is excellent, model is working. But if it is less, so model is not that much good enough for or particular model is not a particular good enough or the valuable tool to predict the things. All right, that is the logistic regression. All right, now we just comes to the model where the we have the values, uh, means y is going to take the values as a count, means 0, 1, 2, 3, 4. All right, for examples we are having here the number of COVID patients that we had in single day. All right, the number of road accident yearly or the number of bankrupts yearly, etc. that we are having. So we have the possible distribution for such kind of things, that is the Poisson distribution, as we have already studied in the distribution theory. In that one, as we know that the distribution of the mean of the Poisson distribution is equivalent to the lambda. Basically, and Poisson distribution having the property that the mean and the variance is equivalent. So that is basically equals to the lambda. In that one, lambda also can take the values between 0 to infinity. So in that case, we need to take the link function that can establish the relationship between the mean response and the linear predictor. And as we have seen earlier here in the previous slide, when it is going to take the value between 0 to infinity, so at that time log link function is quite good for that. All right, so we are going to take the log of lambda, that is equals to the beta. So beta naught plus beta 1 x should be equivalent to the log lambda. So that is basically going to show that lambda should be equals to the exponential e raised to the power beta naught plus beta 1 x. All right. So in that one, we have the interpretation of the coefficients. So consider two data points x. All right, x2 equals to x1 plus 1. That means these points are lambda x1 is equals to exponential e raised to the power beta naught plus beta 1 raised to the power x1. All right, and lambda 2 equals to basically e raised to the power beta naught plus beta 1 x1 into e raised to the power beta 1. All right. So lambda x2 equals to the lambda x1 into e raised to the power beta 1 that we are having. And we are going to take the log of that one. So log of lambda x2 minus log of lambda x1 equals to beta 1. All right. Why we are doing this one? Basically, we want to see that the increasing of the 1 unit in x can lead us to the increase of the beta 1 in the log of the mean count. All right. If you are going to take the one increment of the x1, so it will lead to you the log of the lambda x1, mean of basically the of the variable, our independent variable. So in that case, three cases will arise. First is when beta 1 is going to be 0. In that one, there will be no effect of the predictor variables. All right, on the mean count. Basically, the mean count still remains same as x is going to increase by 1. When beta 1 is going to be greater than 0, all right, that means exponential e raised to the power beta 1 is going to be greater than 0. That means basically lambda x2 will be greater than the lambda x1. That means basically the predicted variable having the positive effect on the mean of our dependent variable, if it is going to be less than 0, beta is going to be less than 0, that means exponential e raised to the power beta 1 is going to be less than 1. So lambda mean response is having a decreasing mean, that we are having the negative effect we are having. In that one, we have few assumptions regarding the Poisson distribution. First of all, the response variable is a count, all right, per unit of time described by the Poisson distribution, all right. Second is the observations are independently distributed, and third one is the by definition of the mean of the Poisson distribution, Poisson random variable must be equal to its variance. All right, these three things should be there for the Poisson distribution. Otherwise, we will not able to apply the regression, Poisson regression on the uh, uh, Poisson regression on the our given data set. All right. Third one is the log of the mean rate is a linear function of the predictor. Basically, the relationship between the predictor and the log of the expected count is assumed to be linear. Otherwise, we cannot proceed with that one. All right. Right. In that one, uh, after that, we have the regression model for the percentage and the proportion of the data. Means proportion of in that one, few examples are there. Means random variables should be defined between 0 and 1. The range, a proportion of the males having the COVID-19 cases, and percentage of the time devoted to the activity, proportion of the female births, fraction of the income spent on the food, proportion of the sales of the SUV cars, and unemployment rate, poverty rate, etc. These are comes under the regression model for the proportion data. All right. In that one, first question is that can we transform such data to the normality? So we can transform it by taking the log of y upon 1 minus y. That should belongs to the real lines. But there is some limitation about that one. The model parameter cannot be easily interpreted in terms of the original response. First problem is that we will have there. All right. Um, uh, because logistic regression cannot be intuitive in directly the interpretation. Second is the heteroscedasticity. That will be the problem because proportion data often exhibits the heteroscedasticity, especially in the tails. That is basically near to the 0 and 1. The tails may show the much more variability and violating the assumption of the constant variance. That will be the most probably that one problem, and the asymmetry, that is the another thing. It should be asymmetric. Proportion tends to display the asymmetry, which can be a cause of issue that normality based inference, and the transformation may not fully resolve this issue, and leading to the misleading conclusion if the normality is assumed. So that is the basic problem is there. In that one, possible distribution for that one is the beta distribution with parameter a and b, where we are having the estimated expected value of y is a upon a plus beta a plus b, and variance of y is ab divided by a plus b square into a plus b plus 1. All right. In that one, we simply need to transform or reparameterize the model with mu equals to a upon a plus b. All right. And phi, we need to consider a precision parameter uh, that is going to concentrate on the distribution is around to mean. So reparameterize, we need to do it in such a way that we need to introduce a relation between a with a plus b, that is equals to the phi. So if you are going to take expected value of y, that will be equals to the mu, and variance of y will equivalent to the mu 1 minus mu upon 1 plus phi. All right. In that case, the density function also changed. All right. between say gamma phi divided by gamma phi mu gamma phi 1 minus mu into y raised to the power phi mu minus 1 and 1 minus y raised to the power 1 minus mu phi minus 1. All right. So phi should be greater than 0 as a plus b are greater than 0. So, but in this transformation, mu will lie between 0 and 1. All right. So phi is a basically is a precise precision parameter, and mu is the mean of the response variable. That is that will be there. Uh, Now, what is the thing is basically important thing. The higher value of phi is indicates the less variance around the mean. That means basically the data is more data values are more nearby to the mean mu. All right. In that one, we can in such way we can use the logistic beta regression model. Again, we have the different link function for that beta regression model that we are having, that log mu upon 1 minus mu. So mu will be equals to the 1 upon 1 plus e raised to the power minus x beta logistic regression function we can use, because now mu is going to take the value between 0 and 1, phi inverse mu. So mu equals to phi x beta, that is the probability function, and the similar that we have discussed earlier, but there will be a new Cauchy link function will be there that we are going to introduce basically. That is tan pi mu minus 0.5 equals to the x beta. That is basically mu equals to 1 upon 2 plus 1 upon pi tan inverse x beta. That is basically used for the more robust or when you the y is having the extreme values. All right, y having the more extreme values in the data set. So at that time we can use the Cauchy link function. All right. So after that we simply take the likelihood function of the model, and we can find out the maximum likelihood estimate through the some numerical methods as we have discussed earlier. Now we comes to the parametric regression model. That is basically when we have the survival data. Suppose we y is we are having, that is during the time to event data between 0 to infinity. So waiting times, the or survival time or repair time, emission time, or the other economic variables are there. In that case, such data are usually most of the time are positively skewed with the heavy tail, as I told you earlier and showed in the our kidney infection data. It was a heavy tail and positively skewed. So most of the time and most of the lifetime distributions are the positively skewed only. uh, Maybe heavy tail or not, that is a different thing. That depends on the characteristics of the models. All right. And the value of the parameters that they are going to take. So even the transformation does not help to make them normal. All right. So most of the time we cannot uh, make them normal. So in that case we may use the exponential family distribution, such as exponential, gamma, Weibull, log normal are there that we can use. So in that one we can do one thing. In that one parametric regression model we can make some uh, linear assumption, linear transformation that we can do. That is basically uh, uh, our transformation z minus mu upon sigma, where z is basically the log of y, that is beta naught plus beta 1x and sigma epsilon. So in that case, epsilon will follow the exponential family of the distribution that we are having. All right, we are not going to the deep of the how it is going to be established, otherwise it will take more time in that case. So possible distribution that we are having, that are the Weibull distribution. That is one of the best model that we are having. Other models are also there, because we are seeing the Weibull regression model, because as we can see in the previous slide earlier, that is going to take the different shapes are there. I am showing it for the only few possible parameter values. If we are going to change the values, it is going to take the so many different shapes are there. As you can see, it is the decreasing, then increasing, then decreasing, positively skewed. All right. Other, if you are going to increase the uh, uh, value, it is going to take the so many different shapes are there. As you can see, it is the decreasing, then increasing, then decreasing, positively skewed. All right. Other, if you are going to increase the value, it is going to take the so many different shapes are there. As you can see, it is the basically the shape parameters value. So it is going to sometimes it takes the normal also. All right. So that's why it is very good enough model that we can use. All right, for our as a parametric regression in the parametric regression model. All right. So here basically, if we take the values of, all right. So in this one, basically we use the transformation epsilon that I told you. So we just obtain the distribution of the variable regression model, and we can find out the value. Basically, the estimates of the parameters beta naught, beta 1, and mu and sigma through the variable regression model. All right. So that will be the likelihood function. And to compare them, we can use the AIC, BIC, and other tools are there that we have already discussed. Now, if you don't have the question, if you have the question, you can ask. Otherwise, we can move to the hands-on session. Can we move to the hands-on session?
Yes, sir, you can move.
All right. So the screen is visible.
It's visible, sir, but it would be better if the font size is little big.
Okay, sir. Is it fine, sir?
Yes, yes, yes.
All right. So the thing is that I just run the codes in the Google Colab. You may run the codes in the R or R Studio also, but in the R there is a limitation. One thing is there we need some packages. So to run those packages, we need there are some several dependent packages are there, packages are there that also we need to install. So in the R we don't have that. Basically the relaxation that all the package will be installed in a once. In R Studio we can do it with the R Cloud, and to save the time I already run the codes, and because it takes too much time to install all the packages, it will take around 20 minutes to install all the packages. So here first we are going to discuss about the logistic regression here. All right. So we have a very famous data set in the R that is called the empty cars. All right. That data set is there. In that one, we have the several variables, MPG, cylinders. All right. This is data about the cars. For the different cars, we have the car types are there. In that one, we have the mileage, MPG is there, cylinder, dispersion, HP, rate, and other variables are also there. All right, so we are going to take the MPG as our study variable, and others we are going to take as the independent variables here in our study. All right, so this variable is taking the continuous values. So what I'm going to do it, I'm going to convert this continuous variable into the binary case. How I'm going to convert it in a binary case? I'm going to convert it in a using the if else condition, where I'm going to say that I'm saying that in the empty cast MPG variables are going to take the value greater than 0, greater than 20. So it should reflect it as 1. If it is going to be less than otherwise, or it is less than 0, sorry, 20, so it should take the value 0. So after applying that one, so I am having these observation 1 1 1 1 0 0. As you can see in the data set, we have the 21 that is greater than 22, and 21 that are greater than 20. So it is taking 1, and 18.7 and 18.1 is less than 20. So it is taking as a 0. All right. So now I'm going to fit the logistic regression model here. It is a very simple uh, thing to apply the logistic regression model or regression model in R. It's a simple single line command is there. So that we have the GLM model is there. Command is GLM that we are having. Here I'm going to take the my high MPG as a dependent variable, and weight, HP, Q second are the my independent variable that I'm going to take. You are going to simply you can add the independent variables by with the plus signs. You just apply the plus sign and write the variable's name. So that will be included. Data, empty cars that I am taking. All right. Family, I am saying the binomial because it is taking the value either 1 or 0. All right. So I just run it, and after that I just apply the summary command. All right. So on the logistic model, all right, I write the logistic model inside the summary. So I got that one. These summary I got it. Value of intercept is there. Value of WT is there for the variable WT. All right, and HP Q sec for all it is there, as well as we have the standard error with respect to the each variable. All right, and then we are having the this one z values, and we are saying that z values are taking the values that are greater than 0.0, p value is greater than 0.05. That is basically showing that there is none of the variable is having the significant effect on the high mpg. All right, so basically how we are going to interpret these results. So intercept beta naught we are having, that is 1.109 e raised to the power 03. That represents the log odds of the outcomes for high mpg when it is going to take the value 1. All right, high mpg is taking the value 0 and 1. So when it is going to take 1, so when all the predictor variables will be 0. All right, so however it represents the values when all the outcomes will be zeros. For the high mpg is going to take the value 1. All right, in the basically in the given context, the weight and hp is basically the horsepower. um, are the interpretation might not be meaningful, and the q size is the not meaningful as having the zero weight and horsepower. Now just comes to the that one coefficients wt, that is basically the weight of the car. All right, in that one what is there, the coefficient of the weight. All right, coefficient of the weight, that is basically minus 1.745 e raised to the power plus 2, that is basically 174.5. All right, this implies that for each unit increase in the weight, the log odds of having the high mpg decreases by the 174.5. All right, as you are going to increase the weight for one with the 1 unit, so high mpg will decrease. All right, and the horsepower, similarly the horsepower is taking the values minus 2.588. That is showing that for the high as you are going to increase the horsepower by the 1 unit, so the mpg high mpg will decrease by minus 2.588. All right, then we have the qsec, that is basically the quarter miles time of the data, if it is going to decrease with the 1.253. All right, so we are having the null deviance, and we are having the residual deviance also there. We can take the difference of them, and aic is 8. All right, we don't need to calculate, it will automatically provide the aic. All right, fisher scoring we are having basically. All right, that is showing 25. That means basically the 25 iteration it took. All right, to reach to the decision. And now we can find out the predicted probabilities. All right, predicted probabilities are there, and we convert into the binary case because we are going to take the either value 1 or 0. So if the predicted value probabilities are greater than 0.5, so it should take 1, otherwise it should take 0. And we are going to create the confusion matrix by the taking the predicted classes and the actual data from that one. So we are finding here through our that one what we call it true positives are uh, 14, and true false are 18 we are having, and we are going to calculate the accuracy and accuracy is showing 1. That means model is performing quite fine. Now we just go to check the assumption that we are having. All right, in that one we need the different packages. First is ggplot2 we are having. Why I'm running it in the Google Colab? Because when we are going to install the ggplot in our R, it takes 17 more packages to install to run the ggplot2 package. And similarly, the car and desk tool are there. All right, as you can see, we have so many packages are there. All right, to check to run the ggplot, and similarly we are having these many packages to run the desk tool. All right, after that, why we need this these packages? ggplot is for the plotting purpose. Car we are going to use to check the VIF calculation for the multicollinearity, and we are going to use the uh, desk tool for the copes distance. All right, so in that one, first we are going to check the linearity of the our model. So we are going to plot the going to find out the predict values with the link function. All right, and we are going to plot it with respect to the log odds with respect to the weight of the car, and we are finding it is not exactly linear, but most of the values are nearby of the line, so somehow it is linear. And similarly for the horsepower, we are finding somehow fine, and somehow fine we are finding in the with the that one, our other variable, that is basically the uh, miles time. All right, it is not linear here. Relationship is there. Now we just go for the cox distance. All right, cox distance is there. For that one, we have the plot. All right, we need to find out the cox distance. That is for that one we have the that one command cox dot distance. That is inside that one we need to write the model. All right, uh, in that one,
Hello.
yes,
Sorry to interrupt, sir, but your screen is not visible, whatever you share.
it is not visible. No.
I
Okay.
think it's visible for me. Sir, you're showing the codes, no, sir?
Yes, I'm showing the code. Okay,
Yeah,
I just
graph is
Okay,
there.
okay.
Cook
I think
distance is
it's
there.
my problem from my side.
Okay, okay, okay.
It may be because you have pinned the wrong screen. Please try to pin the presentation only.
Okay, sir.
all right. It is fine. All right, it just comes to this one. Here we are finding why we need the coax that one. Uh, this one is there. All right. All right. So in this one, we are going to find out to check the outliers. So we have only not many points are there that are going to uh, outside the line. So we are not that many outliers are there. So that is manageable for us. But now we will go for the multicollinearity. That is the big thing. Multicollinearity in between the independent variables. So we just go for the VIF command. All right, under the package. So VIF values we are going to find out in the logistic model, and we find out the values like 42.08, 158.55, 326.56. All right, we have the values, and the interpretation of VIF says that if VIF equals to 1, the value, these values are 1, then there is no correlation between the predictors. Means all the independent variables, there is no uh, correlation. If it is between 1 to 5, we consider it as the moderate correlation. Means it is acceptable. We are not going to means we can ignore the that multicollinearity. If it is greater than 5, so significant multicollinearity is there, which can make the coefficients estimate unstable, and it can increase the basically the standard error in our model. that is there. And but if it is greater than 10, so it is a serious multicollinearity issue in our model. All right, that definitely we need to address, and we are finding we are having the quite high multicollinearity is there, right? That is quite high, more than 10, 42, 158, 326. That is quite high. That cannot be ignored. But problem is that we need to address it in that one. So we cannot use here the logistic regression. That is the additional thing. Okay. Uh, for this, with these independence variable, we cannot use the uh, logistic regression. We need to move to some other regression. So in that one, possible ways are basically the we have lasso regression is there, all right, or regression is there, that we are going to cover in our next FDP session. Not session, basically the next FDP that we are going to cover in that one. All right. After that, someone asked for the that one multinomial regression yesterday. All right, when we have the more than
Hello.
two classes, right? Yes.
Uh, Hello.
Yes. Yes.
Yes, sir. I want to ask one question.
Yes.
Whatever you fit here or the logistic regression model,
Yes.
from summary of that model, any variable is significant at 5% level of significance, and the accuracy of
Yes.
that model is 1. So, can you consider that model for prediction purpose? Because
No, the thing
no
is that
any variables. Yeah.
See, thing is that first of all, uh, problem is not that is a significant effect or not. Definitely, there is no significant effect, but some effect is there. So we can consider it. That is not a that much big problem if we have the these variables only. Otherwise, we can move to the basically one regression model is there, that is called as the frailty models. As in the beginning, Rahul says that my research area. In that one, what happens? We are having the only a few independent variables are there. All right, cylinder, dispersion, horsepower, dirt, weight, and others are there. But some other variables may be there that are going to basically having the effect, but we either not knowing about it, or we are cannot basically evaluate them. All right, so at that time we just introduce the new regression model that is called as the frailty model. All right, so we can go for that one. But yeah, thing is that if they are not having the significant effect, that is the problem. In that case, we can remove them, and we have other variables also, and we can include them. In that case, we can try for the other variables also, and we can see either they are having the significant effect or not. What we are having, which variables we have taken. Okay, we just try for this one plus.
Okay, but I think that model have the high accuracy. Is it overfitting problem? Uh,
uh, yes,
it's
ma'am.
100% accuracy there.
Yes, that is the overfitting problem. Okay, but at the same time, we have the problem. We are facing the problem of that one, multicollinearity. All right, we have the
Yeah.
DISP plus. Let me add one more. We have, okay, these variables we are having. Okay, just try for this one. Okay, sorry, I need to run the previous also. All right. Now we just check other variables are having the effect or not. No, ma'am. no variables having the significant effect, so we can ignore this one. All right. So for
So
this data,
first of all, I mean, first of all, we should find the whether the correlation between predictor variable is present or not, and
yes,
then
yes, ma'am. Yes, that as sir said in the previous lecture, we need to
yeah,
check all these things earlier first. Okay, if it is not there, so we cannot do that one. All right, we cannot
yeah,
go for the regression model. And in that one, as I said, can I move to further? Or is there any
yes,
other
yes,
question?
yes, sir.
Okay,
Thank you.
thank you so much. All right, for yeah, for the multinomial regression, we need the one package that is called as the NNET package. All right. So in that one, suppose we are going to take the one data set that is the count of the pest. Pest is nothing but basically the living things in some particular area that are having the negative impact on the human beings. All right. So suppose I am going to take the these pest counts 0, 1, 3, 5, 8, 12, and 20 and 7 kind of this. All right. And I'm going to create the category on the if it is on the basis that -1 that is none, 0 low, medium and high. I'm going to make them in the label. After that, I'm going to take the one independent variable that is the basically the temperature. Okay. uh, Other variables also we can use here like rainfall and others. Right now we are going to make it as a data frame, and we are going to use the multinom command that is in the NNET package. All right. After that, we are going to take the pest category, this category as a dependent variable, and temperature is as a independent variable, and we make the data frame because we need to put it in the data. All right. So after that, we are having the interpretation of the results. We got the results that is the if it is low, so it is having the impact -3. If it a medium, having the negative impact minus 29. All right. And the high, for the high, the having the impact of 73 for the intercept, or the temperature is having the positive impact on all these three categories, that is 0.145, having the change of 1 unit in the temperature, and have 0.98 changing of the 1 unit change if you are going to do in the temperature. So on the medium it is going to be 0.98, and if the temperature is uh, going to change with the 1 unit, so we will have the on the high we have the more that one impact of the 2.30 on the that one pest counts. All right. Temperature having the positive impact on the pest count is high, so it is having the more impact. All right. With that one, we are having the standard error of the intercept for each three categories, and we are having the standard error of the temperatures, as well as we have the residual deviance is there, and we got the AIC 25.7943 that we can for if we are having the models, means we are going to use more variables step regression that sir told yesterday. So at that time it will be useful to compare the model, which models we can use. All right, now we can go for the predicted probabilities for the model. All right, and we can predict it. So for the different counts, we are having the for the low we have the different probabilities are here. What is the probability for the low? What is happening means, if we can see in this one, probability is continuously is increasing as the we are going to increase the number of counts. All right. So that is the thing that how we can uh, interpret the results. After that, we have the to interpret the coefficient. We need to find out the exponential of the coefficients that is there. Okay. So changing of the one unit here, we can move to the number of low pest is having the impact of 1.156 on the low pest. If it is going to change in the one temperature one unit, that will having the 2.67 on the medium counts of the pest. Similarly for the high. Now we just go for the regression model, parametric regression model that we have discussed. That is survival. We need the package. All right. Stat is already there. In that one, we are going to take a one data set, that is the data set of the lung cancer, basically. All right. In that one, we just see the data set. We are having the time, all right, number of days, status uh, is basically the about the censored or uncensored data. We are going to ignore it right now. All right, age, their gender, all right, and other independent variables are also there. All right. So basically, now other way to check the uh, structure of the data. First is the head. We can see the variables and first six observation, and also we are having the str command to check the structure of the data. It will tell us it is a numerical or quantitative or qualitative data. All right. So we are going to fit the Weibull model here. For that one, we have the command that is called as SURV regression. Survival regression is there. In that one, we need to put the command survival, SURV. That is going to take as a dependent variable and status. It is uncensored or censored. That is going to take in the uh, dependent variable. After that, we are going to take the independent variables here: sex, age, and pH, EC, ECOG, and the data will be lung. And after that, we need to mention the distribution as a Weibull distribution. Simply, we need to run this line and we need to write the summary of the Weibull distribution. It will provide us the model as well as the uh, impact of the independent variables on our model. All right. Uh, this is the one thing that we need to see, that is the scale. Scale is basically the value of the parameter of the Weibull distribution that we are going to take here. And after that, we have the log likelihood value here that is given, and log likelihood value with the intercept only. We are not going to take the independent variables in that one. All right. And as we can see, after including the that one independent variables, the log likelihood is going to be increase. And in that one, we are seeing the one thing, basically the, as we have you are asked earlier, one of you, significant. So we are seeing that intercept having the significant effect, as well as the sex is having the significant effect on the that one, your lung cancer data, time to cover cure, and your that one pH ECOG is having the significant effect, as well as the scale parameter of the that one, uh, log of the scale parameter of what we call it, uh, Weibull distribution is having the significant effect on the uh, time. All right. Now we can take another distribution, that is log normal distribution. We have several other distributions are there. We can take gamma and others also is there. In that one, you don't need to do anything else. You simply need to change the distribution name here, log normal, and you need to run it, and we will check the we will get the summary of the model. As we can see earlier, we had the sex and pH having the significant effect. Here sex also again have the significant effect, and pH also having the significant, but now the parameter value of the distribution is not having the significant effect on the model. So that's how it is going to be changed. And likelihood is, likelihood value is in compared to that one is less in compared to the Weibull distribution. So for further, we can check the AIC and BIC values of the model. For that one, direct command we are having, that is basically uh, AIC fit Weibull, BIC fit Weibull. Similarly, for the log normal, we are having the values, and we are seeing that with the minimum value of the AIC and BIC, we are finding that the log normal distribution is working much better in compared to the uh, Weibull distribution for the lung cancer data with this these two independent variables. If you are going to include the more independent variables, so maybe result will change. All right, so that we need to check by our own number of times. So that is the impact. So now we just comes to the that one Poisson regression. In that one, we are going to take the one data set that is basically the WARP breaks that we are going to consider. All right. In that one, this is the data set where we have the number of the breaks. All right. And we have the factors are there. All right. So in that one, the command is simple. That is basically GLM again. And we are going to take the breaks as the count of the earned breaks. And we are going to take, we are going to modeling it. Sorry for the disturbance. All right. Wool and the tension as a predicted variable. We are going to take these two variables as the independent variables, and we are going to apply on the break follows that one. Basically, the independent variable is the wool and plus tension. The family we are going to take basically the distribution as the portion, and we are going to the link function as the log link function we are going to use here, as we have discussed in the theory earlier, and data will be the warp breaks. All right, and simply we need to run it, and we will get the summary of the fit position, and we got the results here. All right, intercept again 3.69196, that, and with the standard error, very low standard error we are having, and these are all three variables are having the significant effect. All right, on the variables that is called as the Poisson regression. Here null deviation is there that we can already are having with the 53 degree of freedom. Residual deviance we are having, so we can calculate the deviance with the help of these both of these, and we are having the 493 as a AIC values that we are having. All right, so we can proceed in that way in the Poisson regression, and others are there. I will share these all the codes with all of you. All right, I will share with the Rahul, and he will mail you all the codes right now, so you can do the hands-on. I didn't send it because it will take them more than 20-25 minutes to install the packages. These all packages that we are having. If you are having any questions, then we can go for the discussion now. I hope.
Hello. I
Yes,
have one
ma'am.
doubt regarding the parametric regression. That is in our
Yes, ma'am.
logistic regression, we make a conclusion based on the odds ratio.
Yes,
Then
ma'am.
similarly in cost proportional hazard, we make a conclusion interpretation based on the hazard ratio. Similarly in parametric regression, is there any such a statistics used?
No, ma'am. In the parametric regression, we don't have that one. Kind of odd ratios are there. Means basically the ratio. We can simply directly says that changing in one unit of the value of xi, we can see that much of changes in the values of y. Basically, the distribution is there. Uh, we don't need to make so many transformation most of the times to make it linear, because it's basically considered as the non-linear only. When you are going to include the distribution
Yeah.
in that one, it will be the non-linear only. It will be the part of the non-linear.
Okay, sir. But I have understood that is in hazard ratio we defined as e raised to beta. Similarly, the odds ratio is also we defined as an exponential of beta. That is when we using any statistical software like SPSS, we got the output as parameter, estimate standard error and the corresponding p-value, and another column is the EXP beta.
Yes, ma'am.
That is in logistic and hazard ratio is the same way we interpret. Similarly, in the parametric regression model, we also get the value for the beta. Is there any meaning of taking the exponent of that beta?
No, ma'am. In the parametric regression, when you are going to choose the distribution, na,
Uh,
we can ignore that one in that case.
okay, okay.
All
That is
right.
in AFT modeling, we use the some acceleration factors in AFT model.
Yes, ma'am.
In the AFT model, we use the exponential of that parameter as a for the interpretation. No?
I didn't get it clearly, ma'am. Can you just repeat it? The model I didn't get. What model
That
you
is
said?
accelerated failure time model is there.
Yeah, accelerated
Uh,
failure time model is there.
uh,
Yes, ma'am.
then in that model, how can we make it in the conclusion about the significance?
In the accelerated, ma'am, basically, it is at that time you don't need that one, ma'am. In the accelerated
Okay,
failure time also,
okay,
we can
okay,
ignore that one at that time. All
okay,
right. It is basically when we have the uh, that is basically called as the threshold effects. Basically, all right, means we have the stages are there. So at that time we need that one. If we are not having that kind of stages, so we at that time we ignore that one. If we are
okay,
going to say it in the stages, means if we are going to convert in that one the continuous variable in the that one basically the categories, at that time we need that one.
okay, sir.
Yes, ma'am.
One more doubt. In logistic regression, we applied when the response variable is a dichotomous and the explanatory variable may be continuous or categorical.
Can you repeat, ma'am?
That is, the logistic regression is applicable when the response variable is dichotomous, that is
Yes, ma'am.
binary, and the independent variable may be continuous or categorical.
Yes, ma'am.
That is
See,
when
we
the
don't have the any foundation or any particular limitation or particular assumption about the independent variables.
okay,
Independent variables can be categorical, can be count, can be that one.
okay.
Basically, the continuous.
Then my doubt is that when the independent variable is a categorical one, then how can we make an interpretation based on our odds ratio? That is when will be continuous one, then we make a unity increase in that value. Uh,
Yeah, basically, it is like that. Uh, when odd ratio we are taking, so it will say that if it is zero, okay,
yeah,
suppose we are going to say zero
yeah,
and one.
yeah,
Okay.
uh,
So when we are going to find out the log odds na, through the beta,
uh,
so we
uh,
say that this is the probability that it will go to from this stage to that particular stage.
okay, that
Means
is
if I'm saying that, if I'm going to say that, suppose someone is going to having the so many abortions. All right.
yeah,
So what is the and we are going to check that they are either they are fertile or not fertile.
yeah,
Okay. So we
yeah,
say that if the log beta we got, so we say that they will be go to the fertile to not fertile with this particular probability. Okay, through the log odds, we say that they will move to the another stage. Means with the help of the that one log odds, we say they will move to the next category.
okay, okay.
Yes, ma'am. That is the basically thing is
That is when we are using the R codes, the explanatory variable may be quoted as 0 and 1. Okay.
you just mail me. I have the detailed interpretation of kind of
Oh,
that you are asking, na, ma'am. The
yeah,
independent variable having the that one
yeah,
categories. So
yeah.
regarding that, I have the detailed interpretation. Okay.
Okay.
So I
Okay.
will share that detailed interpretation with you. So it will be easy for you to understand. I have
Okay.
for both continuous and the categorical.
Okay. Okay, sir.
Yes, ma'am.
Oh, thank you, sir.
Thank you.
Hello.
Yes, ma'am.
Hello.
Yes, ma'am.
Sir, I have a question related to Poisson regression or exponential regression. How to decide whether the Poisson regression is good for that data or exponential or variable distribution for that data? So how to decide if we have a data
Okay, how to choose
in
the either the
in
Poisson distribution or the that one exponential or
yeah,
the gamma or Webel, right?
which
So when
distribution is the best fit for that data?
which distribution is the best fit is basically depends on the ma'am. We should start from the very basic, from the exploratory data analysis. First of all, first we should
Yeah,
need to check the nature of the data. Okay, as for
yeah,
the Poisson regression, we says that it should be the count. Okay, it should be discrete.
Yes.
Okay, it should not be
yes,
continuous. If it is continuous, definitely we are not going to use the Poisson regression, right? So
yeah,
first thing is that after that we should plot that one. Okay, are it is going to fit with the Poisson distribution or not? The count. And for the count, we have only
yeah.
one distribution, that is the Poisson distribution in the theory.
Oh,
But for the exponential and Webel and all these others, basically the what we call it parametric regression. What is the thing? Thing is like that. We need to check the shape of the data. Okay,
yes.
means it is going to match with the shape of the exponential. As we have the, I showed you that one in the PPT for the exponential. Give me a second. I just show you. I prepared that one gamma and others also. Where is the gamma
You mean
also?
we have to draw the probability density function for response variable, and whatever the shape,
Yeah.
then,
Yes. I just
this,
give me a second. I just share you. I just show you the that one.
yeah.
Mm, okay. See, as the Weibull distribution is there. Is it visible for you, ma'am? The PDF of the
Yes.
Weibull distribution.
Yes, sir, it's visible.
Okay. So we are having the different shapes for the different range of the parameters, right? It is going to be uh, basically the skewed, all right? It is going to increase then decrease. So if this kind of shape is there, so we can go for the Weibull. Okay, first thing. Now, sorry. And if we are having Weibull, and now we have the gamma, all right? Gamma distribution. Gamma distribution shapes are quite different from the Weibull. Yes, ma'am. Most of the values are on the left hand side for most of the cases. It is having the heavy tail, but it is not moving. It is not that have that much of scatteredness is there in the gamma. We cannot see that much of scatteredness in the data set, but we can see the scatteredness in the Weibull, right? Values are far, means it is quite far. Values are there. So in that case, we cannot, if the data is like this, we cannot use the Weibull distribution. Weibull will not produce that much of good results, but gamma can produce. And now just comes to the exponential. Exponential is having continuously decreasing, right? It is not having the increasing case in between anywhere, right, ma'am?
Uh,
Are you able to see?
yeah, yes, sir. But which parameter should we take observing this density
Means
curve? Or
yeah, so that's how you need to check it, which model will be more suitable for it. So actually, what is the thing is that which model we just consider as a good model, that is having the more flexibility. Okay, more flexible,
yeah,
that we consider as a good model. So instead of choosing for the one particular any particular model, so we go for the generalized thing, like generalized Weibull distribution is there. All right, or the Weibull distribution is there. Weibull are quite flexible. If you just see, Weibull is having the both, containing the both shapes, like exponential, whatever the exponential is having, or whatever the that one, our gamma distribution is having. So we can consider Weibull distribution instead of the exponential and that one. We are completely independent or free to choose the distribution. There is no hit and run rule that we should stick with this one. We are independent to choose the models. That's why we don't have any best model. We have the better models always. All right.
Yes.
So we can use
Yes.
any distribution at that time. That is more suitable for our data in compared to the best model. Means in compared to the other.
Yes. Thank you.
Thank you.
So there's a question in the chat box: how to choose specific link function?
How to choose the specific link function? See, can we check the distribution for the dependent variable or the? Okay, wait a second. In that one, basically, how to choose the specific version, that one, in that one, when I just showed the ppt, in that one showed that where what is the range of the that one, basically your mean response. All right, according to the range of our mean response, we need to choose the our link function. We need to stick with this thing. Okay, it should not go beyond that one. The link function we should need to choose in between that range. All right, that is the thing. And the next question is that can we check the distribution of dependent variable or the error, sir? Yeah, dependent variable we can check now. We just simply draw the graph as I showed earlier. We just draw the dependent variable and we can find out it is similar to which distribution, and accordingly we choose the distribution. All right, there is no hidden कोई particular rule is not there that which distribution exactly it should follow. All right, we have the more than 10,000 distributions are there in the literature that we are having. Every day we are getting the new distribution that are having the different shapes, and after changing the values of the parameters, the shape of the distribution will change. So based on that one, we need to check which distributions are will be much better fit in compared to that one. That's why what I did in the same data set, I used the log normal as well as I did the Webble. Okay, and we found that log normal were working much better in compared to the that one, our Webble distribution. If we have the some other distribution, so definitely it will work much better in compared to that also. All right, several other distribution means so many distributions are there that works better than the Weber distribution. Or no log normal also means universal lineage there, generalized universal lineage there. These distributions are there that and top Leone comes and TJ distribution comes. So many distributions are there that they are working much better in compared to the Weber also. But problem is that we don't have the inbuilt commands for that one. At that time, we need to write the manual code to find out the estimation of the parameters. So that will be the problem. At that time, you need to introduce the model by your own. All right, you need to write the likelihood as I have shown in the PPT. We had the likelihood function for all the models. So at the in that some same way, you need to write the likelihood function, and then you need to go for the manual coding instead of the direct command. That is the thing. All right. Anyone else?
Sir, I have one
Yes, ma'am.
question. In some paper, I showed that science literature. I showed that in some they for interpreting the best fit for best distribution. Some papers showed that the AIC value is used for making that the minimum AIC value will be give the better model. Some papers showed that some BIC value they used. Then which one is the better
No,
method?
no, ma'am. Actually, thing is that we can use any tool, AIC, BIC, or we can use the AICC. That is the updated version, updated method of AIC, and we can use HQIC. We can use CQIC. All you can use, and it has been seen, and I have seen it in my paper a number of times. If AIC is less, so definitely BIC will be less, and HQIC will be less, or DIC will be less, or CQIC will be less. If one is less, so others will definitely less. It will never happen that if AIC is less, so BIC will be high in compared to other models.
Okay.
Okay,
Okay. Okay.
means if two models are there, so if one model's AIC is less in compared to other models, so BIC will also less in compared to other models. It will always there.
Okay, sir.
So you can use anyone.
Okay.
Yeah. Anyone else? Okay, then we can conclude, Rahul, I think.
So, thank you, Dr. Shikhar Tyagi, for such an insightful and engaging session on generalized linear models. Your deep expertise and clear explanations have provided us with valuable knowledge and practical skills that will greatly benefit our academic as well as our research work. Thank you once again. And thank you to all the participants who tuned in to join today's session on generalized linear models. The feedback form has been already shared. If you haven't got it, please let us know. We will share it again. Please fill the feedback form and join us once again tomorrow on day 3, where we will be having the session on time series analysis, Introduction to Time Series by Dr. Varun Agiwal. So please join us tomorrow sharp at 6 p.m. Thank you once again. Have a good night.